sir. How are you?
How are you?
Fine, sir. Fine.
So, am I audible?
Yes, sir. You are very much audible, sir.
Okay. Or should I increase the voice or noise?
A little bit of your voice, sir, not the noise.
Okay.
But you would never make noise. You are always voice.
I'll see how to increase. I'll go out for a while. I think I have to go out and increase.
Yes, sir.
Whenever you are saying, I am ready.
Yes, sir. Definitely. Definitely.
Good evening, one and all. On behalf of Department of Chemistry, St. Joseph's Degree College, Kurnool, I welcome all the participants for today's webinar on IR and NMR spectroscopy. Let's start our session with the prayer song. I request our principal ma'am, Dr. K. Shanta, to give her opening remarks.
A very pleasant evening.
Madam,
మేడం మ్యూట్ చేసుకున్నారు
unmute.
Yes, am I audible? Yes? Okay. Today's resource person, dynamic and energetic Dr. A.V. Ramna Reddy sir, participants from different parts of the country, my colleagues, a very pleasant good evening to one and all. St. Joseph's Degree College is governed by St. Joseph's Educational Society. It has been serving with a motive to provide quality education to the students from all walks of life. The institute started off with science, computer science, management, and commerce courses. Currently, the college offers 11 courses in 3 undergraduate programs. The college is self-financed and affiliated to Rayalaseema University, Kurnool. Presently, about 3,500 students are studying in the college, out of which girls are more than 50%. The college has experienced and well-qualified faculty team who always strive to give their best to impart quality education to the students. The college has eminent PhD holders who stand as a pillar of strength to the academic activities. The college is surrounded by green environment and excellent infrastructure in 11 acres, which facilitates effective teaching and learning. The college believes in creating the future citizens of this country and thus emphasizes on values and ethics. Every day, the college begins with a prayer followed by a student giving out a reading an article in the assembly. The institution has earned goodwill due to the long academic experience combined with service motive. The college takes pride to state that it does not collect any donation or capitation fees from the parents. College is an NPTEL local chapter to facilitate the students in getting their certificate courses, which help them in improving their skills. The institution produces university ranks consistently with the effort of eminent faculty members who contribute their fullest for the betterment of the students. The values we impart, along with the education, has been a point of conviction for the parents. Extracurricular skill development programs such as placement preparatory program, yoga, communicative English, tally, etc. are conducted for all students during their period of study. The student activities are supported by various cells and clubs such as NCC, NSS, YRC, English Club, Cultural and Literary Club, Entrepreneur Development Cell, Women Empowerment Cell, etc. The college has an eco-friendly green environment which creates good atmosphere to work and learn. The institution has an excellent play field to encourage the students to improve their sporting skills. The college over the years has constantly registered growth in all aspects. The college aspires to grow further to serve many more students by starting many more courses in future. It's indeed great pleasure and a moment of pride to me, as well as to the learning fraternity, that we have such a renowned person amongst us today. Elia sir, a warm welcome to you. I was fortunate to meet Dr. AVR Reddy, who was leading a team from Baba Atomic Research Center for the conduction of a workshop on radioactivity at SSBN College, Anantapur. In the inaugural meeting of that day, Dr. Reddy, displaying his mail ID on the screen, said that any queries on any other aspect, the participants can mail to him, and he would be replying the mails only on Saturdays because of his tight schedule in the weekdays. I was surprised that Dr. AVR sir has replied me so promptly when I mailed him asking for a clarification in NMR. He is a man of commitment, dedication, and great passion to teach. His zeal to learn from people he meets is incredible. Sir, I am overwhelmed to have you here on this platform. Thank you so much. I can assure every participant that you will have a great wealth of knowledge to carry from this session. So, dear participants, please get ready for the valuable session, which is going to take off in a while. Sir, I immensely thank you for accepting our invitation. Thank you very much. Over to you, Vasavi.
Thank you, ma'am. Now I request our Vice Principal, Dr. C.V. Satyanarayana sir, to present the outlook of today's webinar.
Good afternoon, dear participants. Sir, good afternoon, sir. I'm seeing you for the first time virtually, sir. But I heard from Shanta madam very long back about you, your energy levels, your another way, like say, comedy quotient, your knowledge in sports, and many more things, sir. So today I'm able to meet you virtually. Hope so. I'll meet you personally sometime to really feel the transfer of your energy to the people like us, sir. And today I think I'm going to be a part of this. I'm a part of this program, learning something about spectroscopy, though it is not my
Cup of tea.
frankly speaking, cup of tea, because I'm from the Department of Computer Science. But still, the spectroscopy is a subject which I heard many times in our discussions, being a vice principal, when we get into the discussion with our HODs. They speak more about spectroscopy and the spectroscopic devices, the history of the device, the usefulness of the device and all. Still, I don't understand the practicality or the technology for which actually it is used. But from what I understood with Shanta ma'am's discussion this morning is that it is used to analyze the molecular properties of the
Structural aspect.
structural properties of the items, or let me say the material. So that's what I understood, sir. But I'm part of this webinar only to listen to you, sir. To feel your energy and get motivated. Because even at this age, you are really so energetic with a bright smiling face. Really great to see you, sir. So it gives us a lot of energy for us, for even the participants also out here. So let me hope I'll be definitely meeting you personally to feel the real energy, sir. So thank you very much, and I congratulate the Department of Chemistry for organizing this beautiful webinar to a beautiful person, a knowledgeable person. Thank you, sir. Thank you very much, and all the best to the participants. Thank you.
Thank you, sir. Now I call Ms. Sai Suma, lecturer in chemistry, to introduce our resource person, Dr. A.V. Ramana Reddy, sir.
Shake చేస్తున్నారు సార్. Shake చేస్తున్నారు.
Good evening to all. I'm Sai Suma, lecturer in chemistry. An immense pleasure to introduce Dr. A.V. Ramana Reddy, sir. Dr. A.V.R. Reddy graduated from Bharat Training School in 1976 to 77. Dr. Reddy was a professor of Homi Bhabha National Institute. He was the president of Indian Association of Nuclear Chemists and Applied Scientists. He was the former head of Analytical Chemistry Division at BARC. His areas of research are nuclear fusion, nuclear.
Now continue.
So good evening to all. I'm Sai Suma, lecturer in chemistry. It's an immense pleasure to introduce today's resource person, Dr. A.V. Ramana Reddy, sir. Dr. A.V.R. Reddy graduated from BARC Training School in 1976 to 77. Dr. Reddy was a professor of Homi Bhabha National Institute. He was the president for Indian Association of Nuclear Chemists and Allied Scientists. He was the former head of Analytical Chemistry Division at BARC. His areas of research are nuclear fission, nuclear reactions, nuclear spectroscopy, heavy element chemistry, nuclear activation analysis, speciation studies, electrochemistry, and general analytical chemistry. He has about 700 publications to his credit. He is a co-author for 4 books, edited 22 compilations and books, and wrote chapters on nuclear analytical techniques in 3 books. During 1992 to 93, Dr. AVR worked in the Institute of Nuclear Chemistry, University of Mainz, Germany, on the chemistry of transactinide elements and extension of the periodic table. Dr. Reddy worked as a technical officer in International Atomic Energy Agency in Vienna during 1999 to 2000. He is a member of many scientific associations, vice president of Association of Environmental Chemists of India, a fellow of International Union of Pure and Applied Chemistry, and worked for 3 terms during 1996 to 2002 on the IUPAC Commission on Radiochemistry and Nuclear Analytical Techniques. Worked as a member and secretary for BSc, BRNS, and member of Program Advisory Committee, DST. He was also ISO lead author and audited international labs. He is in the editorial board of many national and international journals. He extends expertise to the collaborators from different universities in India. In about 40 countries, Dr. AVR has delivered lectures and also in many Indian institutions. Currently, he is the CEO of Gemological Institute of India, leading a research team under his supervision on spectroscopy to determine the purity of gems and other precious stones. Dr. Reddy is a kind-hearted, humble man, always ready to help the needy with his experience and knowledge, and he is an excellent teacher. With this quality, he teaches, educates, and empowers the students and enthusiastic people who intend to upgrade themselves. Sir, we are really blessed to have you today among us. Thank you, sir. Over to you, Vasavi ma'am.
Thank you, Sai Suma. Now I request Dr. A.V. Ramana Reddy, sir, to present the discourse.
Thank you, sir.
Sir, unmute yourselves, sir. Unmute yourselves. No. You're
Okay.
on. Yeah.
Okay.
Yes, sir.
Good afternoon or good evening to everybody. Many thanks for exaggerated introduction of myself. By listening to my CV, you may be wondering a nuclear chemist like me, what am I doing with organic spectroscopy? That you can judge after I complete the lecture. 1 year I taught organic spectroscopy. This is Dr. Shanta has invited me while talking to me. She told it is meant for undergraduate students. Therefore, I kept it at slightly introductory level. And probably if any one of the participants gets some doubts, as she suggested, you can write to me, particularly about the elucidation of the structures. And I'll spend time with 1:1 or WhatsApp call or whatever it is. Now, regarding the talk, let me now share the screen. We'll move on because this brief introduction took away a lot of time. This syllabus is extremely large. Your college syllabus itself is for 8 + 8 hours. I have to complete in 1 hour. I don't believe in syllabus completion of the syllabus, but let me convey something to the participants. Okay, now yeah. Okay, I will come to that.
टाइम में आता है वो एक घंटा है वो भी का चौंद्रे के बीच में हो घंटा चौंद्रे के बीच में हंदे भी
Shall I start? If all the participants keep quiet, life will be easier. Okay, thank you. This is the first part of this is the title, and the first part I'll be covering about IR spectroscopy. Before that, since the students are the participants, I thought I will share with you how to learn, particularly science education. See, there is a difference between literary person and educated person. So we have to think about education. Therefore, question. Since most of you know Telugu, prashna chaduvula talli. Questioning is the main way of learning. Therefore, we have to question. My teacher taught me first 2 questions. Remaining 3 I formulated. Always I believe what I see, we should have a keen observation to know. We should have curiosity to understand. Then we have to develop the reasoning. Then, of course, it is always, collective learning is easier. Share the knowledge with the friends and teachers, and finally give a seminar. Demonstrate that you know. The day you stand before the students, you learn more. A teacher learns more than the taught. I believe that, and it's true. At the same time, for the students, I advise not to get pressurized. Plan your issue, whatever is the problem, in small steps, organize it, execute, but monitor. If you don't get the expected results, don't worry, replan it. This is the way one should learn. So I always tell this before I start. Now, as far as the part 1, that is IR spectroscopy is concerned, I thought I will start with a small introduction to spectrometry, general instrumentation, one slide, and electromagnetic radiation. Because when people are asked in the incoming interviews to BRC, many people fail to answer electromagnetic radiation spectrum. Not that they don't know, the clarity. What is missing is clarity. And I also believe that everybody is intelligent. Only question is that believing in yourself. For that, one has to work a bit hard and listen seriously. Okay, now come back to this is the electromagnetic radiation. I will just show one slide and explain the important regions. Then, of course, I give one slide which is very important, various regions of interest. and then corresponding energy and frequency I will show you. And then I will tell what is the instrumentation we can go through and utilize that region to exploit, to measure or to analyze or to understand. These are the three things: quantitative, qualitative, and overall understanding. Then after these 4 or 5 initial slides, I will come to IR spectroscopy, the meaning. Then what is the meaning of absorption? How do we explain the energy through Hooke's law? Then molecular vibrations and its relations to bond strength I will explain in one slide. Then some important frequency values I will show you, and how to exploit IR spectra to enhance our understanding I will tell. Then how to measure and get a spectrum I will show only qualitatively, because all the instrumentation I have removed except one photograph, and I will list the fingerprint frequencies. Then what are the trends of energy and intensity for different bonds I will show. Then I will show a few spectra and one homework question I will give. This is the part 1. Part 2 I will tell when we go there about NMR. And you all know that spectrometry and spectrometric methods, you know the meaning of it. The moment you say spectrum, on one axis, x-axis, you will have the independent variable. On y-axis will be the dependent variable. That's all the spectrum. There are various things. As far as today's lecture is concerned, x-axis is energy, y-axis is intensity, right? When we go to the IR region, we use the centimeter inverse. There's a frequency. Whereas when that meaning, there is a meaning for it. What is the meaning? Why we are using frequency? When we go through, you understand. When you go to NMR, we use some relative scale. When you talk about UV, we talk about wavelength. When I go to nuclear spectroscopy, I put energy straight because energy units are very high. So generally, the probe, for any instrumentation, you need a probe which is used on the sample, which I will show in the next slide, and then it will generate a readable signal. Then we use a detector to convert into a readable signal. Then we read it and try to interpret. I will show you in the next picture. So our probe is photons, that is electromagnetic radiation, and very unfortunately, our signal also radiation. So we have to be very careful. Okay, so spectrum, and you are using measurement. We are using the measurement. And when you use the photon measurement, some people call it spectrophotometry. Every word has a meaning, right? So in this, since we are using light, the important characteristics, we all know that wavelength, lambda, frequency, then wave number, and angular frequency. And you know that light has the wave and particle duality. I am not going to go into details. I used to go into details if you are having a 5-6 lectures. This is anyhow for graduate students. So all of you pass 12th class, so you know. Light is viewed as a stream of discrete particles, and we call them photons, right? This is a general meaning of spectrometry is simply variation of an dependent observable like intensity on independent variable like wavelength or energy. That's all the thing. Okay. Now, whatever I have told you, I don't know, top, can you see? This is readable signal generation in instruments. Can you see the top? It's Shanta, you put
Yes,
on
sir.
your,
Yes,
you can
sir.
see the top.
Yes. Readable signal generation.
Whereas I am not seeing, that's why. That's all right, I need not see.
Right.
So this is the thing what I was telling. You have to take a sample. You need a probe that stimulates to cajoles it to get the signal. That's important thing. And here it is, ours is photon is the thing generally. And then a detector that can detect whatever signal it creates and converts into readable signal. And this signal, using electronics, we get into a readout, either as a number or a number as a function of wavelength or straight as a chart. Okay, that source, etc. I need not go through details, right? This is an important point. If anybody has a doubt, You can ask me after the class, even now you can disturb and ask me, no issue. Okay, this is about the generation of the readable signal. So we need a source. That is an important thing. We need a source that stimulates, that manages to get the signal out of this sample. That's an important thing. So we should know the interaction between these two. Again, I am not spending the time because of lack of time today. Okay. And then various detector also I am not covering. And signal generation also. Details I am not going through, but I am telling you these are the black boxes. Okay. Now, about electromagnetic radiation spectrum. It is simply a line. That's all the thing. You draw a line, put wavelength or wave number or frequency, different regions you observe. That's all the thing what we call electromagnetic radiation spectrum. Any chemistry book, physical chemistry, organic chemistry, or physics, you see in the first few pages this line. Then from there are definite zones which are of very important to us. In the next slide, I will give the details. You see, in the high energy region, what we get is gamma rays, which we are not talking today. In the next region is X-rays, very useful probe. And my life throughout, I have spent about 30 years on gamma ray measurements. And then comes a small region, ultraviolet region. And further smaller region is the most colorful thing, what we see, visible region. UV and visible region correspond to electronic transitions in the context of today's lecture, though I'm not covering it. And then the next, there is a quite a bit large, rather long region where this is called infrared, means beyond red. Ultraviolet means below violet, right? And this is VIGBR, this is. So this IR region is useful to understand vibrations. This is our lecture today. Then comes further lower energy microwave radiations. And then the next one is radiation in the radio frequency. That is our next lecture on NMR, part 2. So this is the electromagnetic radiation spectrum, which all of you are familiar, I just reviewed. Now, this is an important thing I want to, all of you take note, and I am going to leave this PPT with Dr. Shanta. Whoever wants, they can copy this, no issue about it. But if you are presenting, please remove my name, because most of my slides are in the telegraphic language. So when you have the change of spin of a molecule, you observe the changes in the energy, associated changes in the very, very, very small. And the energy range is 10 power minus 8 to 10 power minus 6 eV, electron volts, very small. And this corresponds to a low frequency of 3 to 300 megahertz. And this is the region where we measure NMR. Remember that we are dealing with the small change in the energy. In the next part, I will explain this, right? This is an important region, and it does wonderful in diagnostic things of either structure of the molecule or human body diagnosis, many more things, material diagnosis and whatnot. And so far, I think if I remember, 4 Nobel Prizes have come for this NMR, not NMR application, NMR discovery and its different variations. Now, you know that molecules in atoms in a molecule are oriented in different directions. Their orientations will lead to various rotations. And these rotations will lead to different forming energy states. Remember that when you talk about energy state, it is an equilibrium position available for a molecule to occupy. Like you have a cupboard, various shelves are there. The distance between the shelves varies. But as you go upper side, you will have small nearby shelves, right? And you have to remember your Jablonski diagram, right? And these rotations, molecular rotation can be studied in this region, and energy associated with this also is fairly low, 10 power minus 4 to 10 power minus 2. ESR I skipped because it's not relevant here. This is the region, again, spin orientation. This is, yes, electron spin resonance spectroscopy. Whereas here in the orientation changes, again a small energy, this comes into microwave region. Here the importance is the peaks what we observe are very sharp. So we get lots of information about the molecular orientation, but we are not. And this is a wonderful area. Configuration change. See, each one I am writing here is, if there is a change of is the common. If there is a change in configuration, then we observe different energy states, and energy equilibrium states are different energy states you form, and the energy corresponds to 10 power minus 2 to 1 eV. And this comes into IR region. It's a quite long region. It comes to 10 power 6 megahertz or 10 power 12 hertz region. Whereas electron distribution means electron transfer from one state to another state, right? And electronic transitions are associated. If there is a change in the electron distribution by transitions, then you get information about the electronic configuration of the atoms and molecules. And this comes under visible and UV spectroscopy. That is the thing. Essentially, UV visible spectrometer people use. The energy associated with this 1 to 100 eV. It has lots of importance. This region is having lots of importance for chemists. All these few have lots of importance. Now, material scientists are very much interested because any material when you are changing towards the photoelectroics, photovoltaics, then this is the region where you have to measure whether you get a reasonable flow of electrons. Otherwise, for chemist structure and quantitative measurements, this is a wonderful region, UV visible spectroscopy. Today, we are not covering any. Then comes to, again, distribution only, change in the distribution. X-ray becomes a very good probe. And here you get the lots of structural information, but we are not covering. Then, of course, if there is a change in nuclear configuration, it results in the gamma ray spectroscopy. Gamma ray is the probe. So today I will become this again. You read yourself. If you get a doubt, you call me. This is NMR and this is IR. These are the two areas I will be covering. Now, with this, I will move on to IR spectroscopy. And all of you know, if there are two atoms, let us think about two atoms, a molecule of two atoms like HCl or oxygen or nitrogen, right? Two atoms. When there are two atoms, they try to attract each other. As simple as that. If they have a common bond, they try to move towards each other. At some point of time, there will be Coulombic repulsion. So it will go back. It will come back, it will go back. Means it will continue to oscillate across the bond. Let us think about a linear diatomic molecule. Then what happens is there will be an equilibrium position. And that position, because of this vibration, there is an additional energy state, right? And that energy state, let us say, energy difference is delta E. If we probe that, and if you provide that matching energy, then there is a possibility that a molecule in the ground state can absorb that possibility only, because this is the may absorb, may not absorb. Then when it absorbs, it will go to the next state. So if you are measuring the intensity of the radiation corresponding to that energy, then there will be some missing intensity. We call it as that photons are absorbed. Since it is in the IR region, we say IR absorption has taken place. And that is the thing what we will be measuring. Now, we are lucky to have the diatomic molecules, but you have polyatomic molecules. Once there are polyatomic molecules, there can be n number of vibrations. There will be a large number of states. There will be a large possibilities of absorptions. Okay, let us leave at that stage and move forward, and we'll revisit it back. So where this, see, suppose oxygen is there. Both are similar, right? They go back, come forward, go back, come forward. So you don't see any perceptible change. So one of the important things to see a definite change is there should be dissimilarity between the atoms, so that there is a difference in number of electrons, or asymmetry. That part I will tell. Asymmetry means now only I am talking about linear. There are a variety of things which I will show pictorially. Or at that moment, if that molecule can be polarized. What is polarization? You know, water, HOH, right? There is a delta positive charge, delta negative charge. So that's enough, it is an IR active. Suppose it is not, still it can be made polarity can be created. Such molecules are called polarizable molecules. The great Raman spectroscopy, remember, okay? So in any one of these conditions, there is a possibility that there will be an equilibrium position corresponding to IR region. And therefore, if you probe that, or if you illuminate the sample with the electromagnetic radiation in the IR region, there is a possibility absorption occurs. The moment absorption occurs, we see the difference. Beer-Lambert's law, you remember. Then we observe a peak and so on and so forth. So for this IR region, as I already given you, if you change to wavelength, it comes to 2.5 to 16 millimeter, quite long. So obviously low energy, 4000 centimeter inverse to 625 centimeter inverse. There is no hard and fast rule in this range. Some people quote slightly longer, some people quote slightly shorter range. Doesn't matter. Energy depends on the transitions between vibrational energy states, and stretching, what I just explained, stretching leads to higher energy, therefore higher wave number compared to bending. Because it's asymmetry, no? Asymmetry means this need not go in linear. Like water molecule I told, both the hydrogens come this way or they can go back, right? There can be bending, there can be stretching, there can be rocking. I will show all the positions in one slide. So all these things will happen, but you know that to stretch two things further, you need more energy. So it corresponds to higher energy region. To bend, it's a smaller energy. So this will be in the lower energy region. Energy and wave number are directly proportional. Wavelength is inversely proportional. Now, when the bond stretches, you remember, this is very, very important. When the bond stretches, the increasing distance between the two atoms increases. Therefore, that leads to increased dipole moment. Because dipole moment is a product of partial charge or polarizability into distance. So, if we have longer bond length, that is stronger one. Please remember. Okay. And an example I have given OH, right? Here OH I have given you for the dissimilar atoms, and there already polarity exists. That's why water is a wonderful solvent. Okay. Now, these are the various modes of vibrations. This I have taken from a website. You see the meaning here itself. This is symmetrical stretching. This is anti-symmetrical stretching. When the picture itself tells you, this is scissoring, that you know, scissoring, you know, and this is rocking. Both the things move towards one direction. This is wagging the tail, twisting. So all these modes, it is possible that they will create different equilibria states and different energy states. And any one of them, if a molecule possesses any one of them, then we say that molecule is IR active. Okay. Remember here, a nonlinear molecule of N atoms has 3n minus 6 fundamental vibration modes. In addition, you have additions and subtractions. That we will not talk about it now. Okay. So you have a large number of vibrations. Once the atom number increases, and number of vibrations will also increase. Yeah. Now, you think about this one by Hooke's law. You have a spring, or I just explained. If spring force apply, right, then you will be pulling it out until it breaks, right? Whereas if you reverse it, the spring will come closer. So this is an equilibrium position. This will lead to a constant simple harmonic vibrations. It will lead to an equilibrium state, and it will create an energy state. Simple example. Okay. So Hooke's law is applicable. In fact, I have made 3-4 slides how to calculate the bond strength, but I deleted after listening to that. It is for degree college students. Okay. So Hooke's law is directly applicable, and this is the formula that nu bar, that is wave number, or you call, I don't know what you call, wave frequency, you call frequency, is 1/2 pi c square root of k by mu. Mu is the reduced mass. We are talking about two atoms. Okay. And k is force constant. You can use directly bond strength. Okay. Now you see, higher the bond strength, higher is the wave number. Obviously, stronger bond is difficult to pull. And heavier masses, if the reduced mass is high, then this will be reduced, right? And this is velocity of light. Rest of things are simple. Okay. Now, from this, if we calculate, in fact, I have all the 3 calculations for single bond, double bond, triple bond of carbon, and the strength for triple bond is higher compared to double bond compared to single bond. Okay. Accordingly, in the wave number region, you also get their respective signals. Okay. Now, here I want to show you how the frequencies vary. Relative polarities and relative intensities, they reflect in the frequency or energy. So OH, you all know that this is polarizable. Oxygen is there. Compared to NH, definitely compared to CH. Obviously, there are 6 electrons, 2 pairs of electrons are remaining there, and here normally 2 extra electrons are there. Here it is not so. Generally, all 4 electrons participate, right? Okay. Therefore, this will be more polarizable. Therefore, this will be creating a stronger energy level. Okay. And now you see here, this frequencies, whatever are calculated, are given here. For a triple bond, it is 2150. Remember, higher frequency means higher energy, stronger. And please don't get confused. Triple bond is easy to undergo reaction. Doesn't mean it is weak, right? Triple bond is easy because there are electrons are freely available, they react. Whereas double bond, it comes at 1650. Generally, plus minus 50 you have to add depending on the total structure. And this is further lower, CC. And similarly, here you just see CH 3000, CC 1200, CO 1100, and CCl 750, and so on and so forth. Here, mu is increasing. Once mu is increasing, I showed you in the earlier formula that k by mu, which is in square root. So higher the mu, lower will be the frequency. So frequency accordingly it changes. So in fact, if you want to see a hydrocarbon, first you look for a peak, an absorption peak around 3000 centimeter inverse. Okay. Now, so what is the general information you get from IR spectra? Suppose you have an IR instrument, right? What is that you can use? One is most important thing, structural information we get. That is the first application. Then you can use it also for chemical analysis, right? And for quantitative analysis also we can use, though it is poorer instrument compared to UV visible, as far as the quantitative analysis is concerned. And also it is costly. So if you have to use it, you use it. And you get the electronic information, which is very important, particularly when you talk about optical conductivity and band gap you can measure if you have total reflection IR spectrometer. Band gap. Nowadays, people are preparing the materials, and People are moving these materials towards the, trying to modify them to move towards the semiconductors so that we can develop the photovoltaics, particularly organic mixtures. That means you need the band gap. Semiconductor means band gap should be between the conductor and insulator. So lower is better because it can absorb light and produce an electron. Then once electron is in flow, then you talk about the electricity. Okay. So this is the thing. This is the one of the important applications. For example, in my laboratory, we used to use one ATR exclusively for the band energy determination. Now, what is an IR spectrum? An IR spectrum, as I told in the very beginning, is a plot for any spectrum, a plot between intensity versus wave number. Intensity directly we don't measure because absolute intensity is difficult. Remember Beer-Lambert's law, whether you measure absorbance or transmittance, which is related to the initial and final absorbances. That is, I have written here I out or I in. Means you need a source whose strength is known as I, then that one, I original, right? That one, here it is written as I in, one and the same. Then you make it into two parts. One will go through a blank sample, other one will go with the sample and compare both of them. You get the either transmittance or absorbance depending on the formula what you are using. Now on the x-axis, you use the wave number or energy, generally wave number, and on y-axis, you use the transmittance, right? And then you get the IR spectrum. So, sorry. Now this is just I gave here, if you have 100% transmittance, what does it mean? Entire beam has passed through the molecule or the set of molecules, what you have taken or sample is IR inactive. If it is 0%, means it is a total absorption. Both the scenes can be there, but rare. Okay. So 100% transmittance means there is no absorption. IR instrumentation is no use for that. No polarity at all. No polarizability. So 0% transmission means it is not useful for liquids, but for solids it is very useful. You start from some transmittance and move on, and then you, depending on that, the moment you reach 0%, then you say, yes, this can be used for in photovoltaics, right? Not in everything. There are some applications. For example, in my present institute, if I see saturation, I use for the solids. If I see saturation means this, not only this color center is there, it is fully saturated. It cannot be modified further. That note we will give. Okay. So there are applications for every scenario, right? Now, this is the typical IR spectrum. Wave number versus transmittance is plotted, and we can find out different, see, this is 3000. It should be SEH, right? And there are various bonds, and all these bonds will give you some information, but it is impossible to analyze all the peaks. It is not wise also. I'll explain it. That's why we use the fingerprint region, characteristic peaks, and utilize it efficiently. Now, how we get a spectrum? It's a simple thing. I mean, to tell it is simple thing. Experimentally, it is slightly difficult. If you permit, I will take water. Okay. You mount a sample. How to prepare sample? I have given one slide. You mount a sample, and on that you send the probe. As I told you, you keep a source in the form of a beam of a given range of wave number, right? That all you will come to know once you go to the instrument. Now, When it passes through the sample, whatever comes out, you measure. But initial strength, you know, final strength, you measure. But a better way is either you use a chopper, which will allow once onto the sample, once directly to the detector. So you get the original strength and final strength. Or you split the beam into two parts using a mirror and use them. There are variety of methods, but the principle is you need a source. You should make the sample, carefully prepare the sample, and you need a detector. Rest of the things are simple, electronics, and you observe a chart like this, frequency versus either absorption or transmission, generally transmission. So you get the spectrum. Okay. Now, this is a typical photograph of an IR spectrometer. Unfortunately, I have shown FTIR. So this is an IR for 2-3 spectra I have shown you, 2-3 instruments, which I had in BARC. Now, you have to remember, I told in the very beginning, rather a few minutes back, that you have to measure the sample holder. Means you take the sample in a holder. Let us think about a sample you are taking on a holder, and then blank holder also you have to measure, because in the air also you have a lot of nitrogen. It is IR active. So you get a peak, right? So that is why always you take once with the sample, other time without the sample. So when you take without the sample, you get a background picture like this. And this will interfere with the actual sample. That's why you should have an electronic provision to take both the spectra, one with the sample, other one is without sample, simultaneously. And then you should have a provision in your computer or whatever is the electronic unit to subtract. So background you have to subtract, because background will come when there is no sample. When there is sample also, background will come. It won't go anywhere. Therefore, you have to subtract that. So I'll show you one spectrum. This is the same thing how to take, I have told. This is the thing. You see, this black line is the background spectrum. And this red line is combined spectrum. When you subtract from each other, you just see here, such a nice peak is submerged here in the background. The moment you subtract, you will get a nice peak. Green color is the actual spectrum. So this is the way it is done. If you read here, you slowly move a chopper and allow once onto the background, blank sample, other one is actual sample. Then you get you get two spectra. Instead of seeing both the spectra, it is only for clarity I am showing. Here, green line only we will see finally in most of the spectrometers. Otherwise, you may get confused. Whereas when we started about 40 years back research, we used to take plot background, plot the combined one, then subtract. It used to be a full day job for one spectrum. Today, you get it in 2 minutes. So instrumentation-wise, computer-wise, you have enormous facilities, but working hard, that you have to inculcate. That is the thing. Okay. Now, the next one. See, one of the things what we have to remember is sample preparation is an art, because IR energy is very low and you are using in the energy mode, that is frequency measurement. We have how to make as thin sample as possible. So gas samples can be taken directly, but if you have liquids, always they are taken either on salt plates, if they are organic, on sodium chloride or KBr, generally KBr, to form a thin film. Again, that is an art. Then if they are solids, you mix with an oil and that nozzle, then you pelletize it, then you measure. Or on KBr, you mix with the KBr powder and then compress it. Then first you make it uniform, then use that. These are the methods. I won't spend much time. I just wanted to give an idea that preparation of sample is very important. Yeah, and you should remember that nozzle is one of the wonderful material but it has its own absorption frequencies. So those areas you have to reject even if your signal is there for your sample. Okay. Now, ATR anyhow I won't be covering. Okay. So now I will give you quickly a list of the stretching frequencies which are very, very important, and you can read for yourself. C triple band N, this is the region you have to look for. Intensity is medium. C triple band C, you get around this region, 2260 to 2100. See, there is a lot of overlap. You have to be very, very careful. C double bond C, 1680 to 1600, and C double bond N, you get this frequency, and so on and so forth. I have given quite a few important frequencies, and you should have library for this, and most of the instruments come with this library. Otherwise, you should be in a position. But if you are experienced about, let us say, 10, 15 days, if you work, you will remember these things. There won't be any difficulty. The moment you see a ketone peak, you will never forget. I mean, CO, carbonyl group. This is a wonderful thing. I will explain in the next slide probably. This you have to, I mean, you will not forget. The moment you see, you will tell that. Okay, in a complex spectrum also. So I listed these frequencies. These are all fingerprint frequencies. And now the same thing I have given in a pictorial form, right, for functional group information. And now I have given a homework for you. Last two projections you use and mark at least 5-6 characteristic functional groups in your as homework. This you can copy and find out, then you will feel happy. And particularly mark in this region, mark in this region, mark this. 4 or 5 peaks, then you feel happy. Okay. Now remember, this is the thing what I told. A polyatomic molecule will have large number of vibrations, and therefore IR spectrum will be complex. And we rarely have the diatomic molecules. Therefore, you will land up with large number of atoms. I gave one example. Normal butanol has 39 absorption frequencies, and one should not try to identify every peak. It is foolhardy. All peaks need not be identified. Instead, intelligent way is to look for characteristic frequencies, what we call fingerprints. Okay. In this is OH. Easiest thing is OH and CH. You will come to know sp3CH. You will come to know. As I told you, all this is based on the partial charges or polarizability. So sp3, sp2, sp1, all the things will come into picture. Okay. Lone pair of electrons, so and so, all considerations. But that, suppose you do MSc and organic chemistry, you will come to know. By the way, I am not an organic chemist. Okay. Now, light, here there are some trends I have written here. Light atoms vibrate more rapidly. Multiple bonds vibrate more rapidly. And I have given here the corresponding frequencies. Triple bonds vibrate more rapidly than double bonds and single bonds. I have shown already in the case of carbon. Stretching is having higher frequency than bending, than wagging or twisting. Fingerprint region is, this is the thing very important, 1500 to 400. And also 3000 area don't ignore, right? We deal with a lot of CH rays. And there are many bands and many overlaps. You have to pick up the things. And intensity trends are given on y-axis. You know that polar bonds absorb strongly. That is important. That is an obvious statement. When I say dipole moment is important, polar bonds obviously, and polar bond means dissimilar atom. Particularly one atom is electronegative atom, 4th, 5th, 6th group, and non-polar bonds absorb weakly. And though these are having good frequencies, but their intensity will be lower. Follows overlapping bands. CH bands tend to overlap, and organic molecules contains many overlap bands. But try to ignore them. But there are some cases where overlap bands also help. Okay. Now, how to analyze an IR spectrum? as I wrote in the beginning, first and foremost, you look at CO group. CO group is very important because carbonyl is a distinctly strong peak and you get a distinct peak. If it is not there, then you have to go for other things. If it is there, like carboxylic acid has a CO group, acetone has aldehydes have, right? And ketones have, aldehydes have many more things, right? And then look for whether you have OH. Then look for whether is it a carboxylic acid. Then look for NH combination. If it is present, then look for anhydrides, then aldehydes. In fact, I have a dozen solved problems for some class I prepared, but unfortunately we don't have time. So easily we can identify. It's a thrilling exercise. If you solve mathematics normally, you enjoy, or computer program you enjoy. Like that you enjoy this also, a very logical subject. And once these are not there, then only look for the other ones. If CO is absent, then look for this region, because OH. This OH is a broad band. Look for it. Then go on combinations. That is the thing. By combinations, you will be in a position to identify any spectrum, very comfortable. And if you are lucky, you have a mass spectrum data, very easy. If you have NMR, further easy. These three together, structure of any molecule can be elucidated. Now, double bonds and aromatic rings after that as next priority. Then, of course, look for the triple bonds, then nitro group, then hydrocarbons. All have, fortunately, characteristic frequencies in that sequence. So, first CO, that's very, very important. Then you will be in a position to solve without taking recourse to molecular spectra, even NMR. For most of the simple molecules, you can solve with IR itself. So, Santa, do you have an IR spectrometer?
Sir, we don't have IR spectrophotometer, sir, with us, but we have a double beam UV.
Okay, fine. No, otherwise, this is worth an exercise to carry out. Okay. Now, I am now moving on quickly because one more part is the lecture. So there actually I have to spend a few minutes on the concept of NMR. So aldehydes, I have given an example here and I have shown the characteristic peaks. What I suggest is all the participants, please copy this whatever way you can copy. And I request Shanta even to give this to people, right? And then I have marked
sir.
some.
Definitely, sir. I'll.
Yeah. And then I have marked a few characteristic fingerprint groups that will give you some idea. First, you try as if you have not seen it. Then, of course, you look into it. Then it will become an exercise. Then here I have given one benzaldehyde spectrum. And you see, as the number is increasing, spectrum complexity is increasing. Then, of course, ketones. This is the peak what I was telling. You cannot miss this. You see, in this here, aldehyde, it is at 1731, here it is 1715. Please do not bother about, as I told in the beginning, plus minus 50 wave number, frequency, you should not worry. But the shape of the peak, that's important, and the clarity with which it exists. That tells you that it is carbonyl. That is very, very important. Now, in the next slide, I will show a few amines. And again, in the amine, there is a different story about the broadening and the complexing, and that you will understand with time. But this, I am just showing that you have a feel of the spectra. But explaining this IR spectroscopy, I taught in 30 hours in an university. So in 30 minutes is difficult, but you get a feel of it. Now, and I have marked everything. Now this carboxylic acid, again you just see here, it is 1721. Remember that CO is accompanied by OH. It will have an influence, electronegative atom. So there is a change in this, right? Again, this is, you just see here, ester. Ester also you have. So on and so forth. All these things, you get a feel. Here mainly, you have to get the feel of CO and the influence of the presence of other groups, right? But it is distinctly dominating. Everywhere you just see carbonyl group is there. So when you get an IR spectrum, please look for CO, whether it is there or not. Then only go for other things. Okay. Now, alcohols, of course, OH, I told you, very broad thing you get, right? And when you get this, and immediately you can tell, yes, there is somewhere OH. Very, very easy to identify, right? And along with that, a combination of some bands will tell you the structure. Now, this is again, it's a continuity, right? And here, you see, this one you just see, right? It is purely CH. And even this has a complication, except this. This is a comfortable area where you can identify this very comfortably. You can identify this is an important thing, right? CH stretch, very important. So you can identify all the things, but go through all the spectra, right? And again, some more spectra of here I have taken a spectrum specifically with an electronegative atom. What is its influence, right? And either chloro, either bromo. If you have access to one book called Pavia, Introduction to Inorganic Spectroscopy, all these things are taken from it. And it's a beautiful book. There is no secret, and this is a wonderful. He's a teacher. A teacher has written the book nicely. Of course, there are 5-6 mistakes. Don't worry, you may not find even. But it's a wonderful book and informative, lot of data, lot of spectra. Okay. Now, this is nitro group again. Nitro group, of course, this is a simple molecule is taken. Therefore, spectrum appears smaller, right? Number of peaks are low because number of atoms are also low. And this is an aromatic compound. Whenever an aliphatic compound is given, simultaneously an aromatic is given so that you get a feel whether there is any change. Okay. Now, I am not spending time on each spectrum because of lack of time. Now, with that, I close this because the next spectrum I have to go through the next topic. At 5:30, I have to close now, Shanta.
You are welcome to extend the lecture,
No,
sir. All
I
are
can extend till
interested.
midnight. If you tell, I will go back and explain the spectra. I have a lot of patience.
Yes, sir. 5:30, 5:40. That would be ideal time, sir.
Because the next one, first 2-3 slides, I will take more time
Sir.
to explain what is NMR.
Sir.
So with that, all the examples I stop here. And of course, I have given the references which I used. I used Pavia et al. Book, Introduction to Organic Spectroscopy, actually. And then Instrumental Methods of Analysis by Skoog et al. For instrumental part I have taken. Instrumental Methods of Analysis by Willardine Merritt. Good old book is excellent. There is one book, William Kemp. That is another good book. Organic Spectroscopy, Introduction to Organic Spectroscopy. There is also a good book, old book, but it's a good book. He's a professor, very well written. So, of course, I thank Shanta for inviting me, but we go to the next lecture. Okay, this one I want to do homework. Assign the structure whose IR spectrum is given below. And this spectrum is more than adequate to assign this structure. Okay, so try your best and write to me if there is a difficulty. Okay, with that I close and I will come to the next part. Yeah. File. Yeah. So now we will come to the second part. This is, this needs a bit of, this is slow, about 25 slides. I will go slow. In this, first and foremost, I will explain the meaning of nuclear spin. Many people may not have gone through it, many people, participants, particularly students. I will explain if you want, I will dictate the nuclear spin meaning, then the precessional motion, then how an external magnetic field will create energy states. Unfortunately, people call magnetic states. There is no magnetic state. They are molecular states only. Resonance absorption, that is an important thing. Already we have seen in IR. Here it is the 3 stages are there. Earlier it is 2 stages. One molecule is there, one illumination of the source. Here it is not like that. A molecule is there. You have to create the energy states with a magnetic field. Then you apply a radio frequency, radiation. 3 steps. I will explain. Then magnetic field strength and energy difference, how it varies. This is an important thing if you want to purchase in your lifetime NMR. Relaxation of excited states and spectral shape, then chemical shift. This is the most important thing. Many people have misconcept. So at least I will explain, and whoever wants, if you want, note down, note, because I gave this lecture probably in about 40, 50 places. Everywhere there is a no, sir, we will note down. Physical lecture. I mean, those days travel was there. I used to dictate this, both the things, nuclear spin, the meaning, and the chemical shift. Okay. An NMR spectrometer I will show. Again, here also sample preparation is important and measurement is important. Just I will give a cursory details. How an NMR spectrum is measured, I will explain you. What we look for in an NMR spectrum, I will give a list. Then typical NMR spectrum I will show you. Then the integration of the meaning and integrals, what it represents, I will explain you. Because since she specifically told it is proton NMR, I kept it only for proton NMR. And actually, these shift ranges are given here only. This by mistake, it remains here. And some examples I will give. Then I will talk about spin-spin coupling, which is another concept which has to enter the head. It's a very simple thing. As long as you don't understand, it's a complicated thing. But it's a very simple thing. I will try to make it as simple as possible. Then a few spectra, I will show hardly 2-3 spectra. This is the plan of the lecture. Now, let us think about this. You all know that if you have even childhood, you played the Bongara Lata, right? Top. When you put the top, it moves in a cone shape. That it will create a cone shape picture, right? It will create a path for it, a 3-dimensional picture for it, right? When it will move, when you provide the energy. Here, this a spinning body, a spinning molecule or spinning atom also precesses along a magnetic field. Now, what you have to, any doubt, please? So, okay. Now you see the first sentence. Every sentence has a meaning. A spinning body, if it has charge, proton, for example, generates a magnetic field. You all know the calling bell principle, right? If you press a switch, the circuit will complete, charge will flow, and magnetism is developed, and bell will go and hammer it, right? The moment bell touches it, circuit is complete, it opens. So here it is, any body that is moving in a closed loop, if it has charge, it will create magnetic field. Thumb rule it is. It creates a magnetic field. Calling bell, you remember always, right? Any charged particle, if it moves in a closed loop, then it will create electric and magnetic fields. Electric field you are applying here. So, sorry, you are not applying anything. It will create electric and magnetic fields. We have to think about magnetic field. Magnetic field. Why are we interested in the magnetic field? Actually, if you, any one of you, for general information, you please remember, if you use the electric field, you call quadrupole mass spectrometer, nothing more than that. But we will not go to that now. So both the things are useful. Now we are talking about magnetic thing. So when it creates a magnetic field, now you apply a magnetic field. Already a molecule like ethanol is having 6 protons. So they will act as tiny magnets. They create magnetic field. Then you apply a magnetic field across it. Then what will happen? there are two vectors. So either they will become friends or they will become enemies. If they become friends, together they will go into one group. If they oppose each other, they will go into another group. So essentially, two groups will be created. This is applicable to if spin is half. If spin is 3/2, it will create 4. It's actually 2i plus 1. Don't worry about it. Now we'll go with the two groups to understand the concept proton. We are with the proton. But it's not a thumb rule. I mean, you please don't say that it is true for anything. No. If spin is half, 2i plus 1, so it is two states. One is together, friends. Other one is opposite. So a molecule that possesses all these protons will be split into two energy states. What is the meaning of split? It will create an equilibrium state. Some molecules will be in the ground state, some will be in the higher state. There is a possibility. But if you
I think there is a technical clinch from at resource person side. So please, all of you bear for 2 minutes.
huh? Hello? Huh?
Sir, you are audible, sir. Maybe
Audible.
there's a signal loss.
There are no power disconnected.
Okay, okay,
Now
okay.
it is, now I will host disabled participant screen sharing. Oh,
Host
my-
disable ayinanda. Yes, sir. I'll make you co-host. Host disable ayinanda.
మీరు ఎప్పుడు దాకా ఉంటారు?
Sir, it is done, sir. You can share the screen now.
Host disabled participant screen sharing. Yeah.
Sir, you can share your screen now, sir.
Yeah. Sorry.
It's
Sorry.
okay, sir. It's okay,
Rare
sir.
thing.
Technical clinch.
Power going is rare thing. Okay. Now, we were talking about two energy states are created. And if you eliminate the sample, there is a possibility that it will be absorbed. Now, certain points we should remember here. The energy difference depends on the magnetic field what you apply. So let me just repeat, it's only starting. So a spinning body behaves like a tiny magnet, and proton is an example, and proton in a molecule also is an example. Then when you apply external magnetic field, it will create two states, and the energy gap between these two states depends on the strength of the external magnetic field. Higher the magnetic field is higher the strength. Now, if you eliminate this molecule with this energy difference falls in the radio frequency region of the electromagnetic radiation spectrum. If you eliminate this with that source that is corresponding to RF region, there is a possibility that it will some molecules will absorb and move to the excited state. So now we observe that NMR radio frequency is absorbed, or NMR spectrum, there is a peak. You see a peak. This is the thing what we have to remember. Two things we should remember here. Let us move away from this for a while to physical chemistry. If we have different energy states in a molecular system, each state will have certain population, Boltzmann distribution. That earlier I was telling that you have to eliminate now. Each state will have different distribution, based different level, number of molecules in each energy state. It depends on the Boltzmann distribution. And if you eliminate the sample, some from the ground state will join to the higher state. And the moment this becomes equal, the reversal will take place, it becomes useless. But what we have to remember here is the number of molecules, that excess population, which goes into the excited state is very, very small. For a 14.1 Tesla magnetic field, it is about 9 in million, very, very small. So, but even this small number gives a wonderful decipherable signal, unequivocal signal. That is the beauty of this NMR. Okay. Now, when we go to the, now we move to the next slide. Now I'll put into the, here you just see whatever I have told. Suppose when you apply the magnetic field, in the absence of magnetic field, all the molecules are randomly placed. When you apply the magnetic field, some will occupy ground state, some will occupy in the magnetic state, what you call next state, which is created because of the applied magnetic field. And this delta E, the difference is delta E, delta E corresponds to radio frequency region. And when you illuminate, a molecule or a few molecules from here will absorb and go to here. Okay, that is NMR absorption. Now, before we go further, I will come back after the next one. Yeah, no, I think we'll complete this and okay. Now, before we go further into details, I want to explain to everybody that like you have electronic configuration, and I'm sure Shanta may recollect, I explained this in workshop also, nuclear spin.
Yes.
First and foremost, the word spin of a molecule is wrong. This is actually net angular momenta of all the nucleons inside the nucleus. It's actually net angular momenta. But some in the beginning, somebody called it spin. It continues to be spin. Right. Now, more than that, that spinning molecule was misconceived as if it is its own spin. Okay. Now, how to calculate the nuclear spin? Like electronic configuration, we have nucleon configuration, both neutron configuration and proton configuration. A difficult concept here is that neutrons have separate sequence of filling, protons have separate sequence of filling, which is very difficult to conceive because it is a dense matter. Nuclear matter is very dense, difficult to conceive, but final results it is proving. Finally, when you make that khavat is there, right? Final taste will tell the how you made the pudding. Rather than making process is not important, or who made is not important. So it is explaining, so this concept is accepted. And you see in the 12 carbon, there are 6 protons and 6 neutrons. Both protons and neutrons contribute to the spin and angular momenta. That you should remember, right? Charge is not a criteria here. Now you see in the case of protons, there are 2 in the first state, 4 in the second state. Unlike in chemical state, if you have in a D5, you have 5 electrons in D state, then the most stable configuration is 5 unpaired electrons. But in the case of nuclear states, names are same. Nuclear states, pairing is the most important. Suppose a D state has 4 neutrons, then it will exist as 2 pairs. If it has 5, it exists as 2 pairs and 1 single. Whereas in the case of electronic configuration, all 5 will exist as single ones, unpaired. Whereas here pairing is the most important thing. And there are many proofs for that. We will not deviate for that now. So in carbon, 6 protons will occupy 1 s half state. Half is J state here. L plus S value it is. 1 p 3 by 2 state. So this will accommodate 4, this will accommodate 2. All are in 3 pairs. So this will not contribute to nuclear angular momentum of 12 carbon. Sorry. Similarly, in the case of neutrons, same story. 6 neutrons are there. So it will occupy 1s half and 1p3 by 2. So it will exist as 3 pairs. Therefore, 12 carbon angular moment, net angular momenta, what we call spin, is 0. And non-zero value is only NMR active. Therefore, 12 carbon is useless as far as NM is concerned. You add 1 neutron here, 13 carbon. Then that neutron will come here. It will occupy here. Then it is occupying a 1p half state. So J value is half. Therefore, so I value of 13 carbon is half. Therefore, it is NMR active. So 13 carbon is NMR active. For proton, no question, because only 1 proton is there. 1s half it occupies, and it is single, unpaired. So its J value is half. Therefore, I is half. So our present lecture is on proton and NMR. So proton is NMR active because its nuclear spin is half. And nuclear spin is different than intrinsic spin, what we talk about electron or neutron or proton. Okay, right. Once this is clear, now we will move on to our energy states business. I have written the same thing. Nucleids with odd mass number A. Mass number A, if it is odd, it can have even number of protons and odd number of neutrons, vice versa. So at least 1 nucleon will be unpaired. And all others, all paired configurations cancel each other's spin value and L value, J value. Therefore, the last nucleon, unpaired nucleon, contributes to the spin value of that atom. So its value will be half integer. Half integer. It can be half, 3 by 2, 5 by 2, 7 by 2, depending on which state it is occupying. If it is occupying 1p half like 13 carbon, it is half. 1s half is half. But 1p 3 by 2, if it is there, 3 by 2 value. In that case, in magnetic field, there will be 4 states. Okay. Now, nucleides with even A, that is, it has 2 possibilities, even Z and even N, or odd Z or odd N. If it is even, it is 0. We have just seen 12 carbon, 6 protons and 6 neutrons. If it is nitrogen, 7 neutrons and 7 protons, odd, it has a value of 1. A combination of these two. It is not simple addition. It is a vectorial combination. Suppose if we are adding a half state with 3 by 2 state, then value can be 2, 1, 2 or 1. Whereas if it is simply half and half, there is no other option except 1. So nitrogen is NMR active. So remember that if the mass number is odd, you can close your eyes and say that it is NMR active nucleus or atom. Okay. And if it is even number, particularly even like 12 carbon and for 16 oxygen, etc., it is NMR inactive. If it is odd, then also it is NMR active. Okay, once this is clear, now let us see how the energy changes. This picture already I have shown. The field, if the field goes along with the spin of the nucleus, then this energy will be lowered. It is a compact structure. Otherwise, it is higher. That is more unstable, less compact. That is the meaning of it, right? So these two states are formed if a molecule like you have a hydrocarbon or ethanol, it is having proton. So in a magnetic field, it will give 2 energy states for each proton. Please remember that, for each proton. Okay? That there will be slight variation, I will tell that, right? And when you talk about equivalent and non-equivalent atoms, we will get clarification. As a first step, we should understand that if you have proton in a molecule, that molecule can be studied using NMR spectrum. Its NMR spectrum can be obtained. Okay. Now here you just see last sentence. If proton is not free, but a part of a molecule, then molecule gets oriented in 2 directions. It is not just proton. Once proton gets along with that entire molecule, in fact, number of orientations, that is number of energy states are 2i plus 1. I gave you already this value. Okay. Now, this is the thing I am revisiting after understanding the nuclear spin. Suppose it is the ground state after, this is the configuration before illuminating, but after applying the magnetic field, in the first state there are, I call alpha, 4 molecules for simplicity. Third, there are 3. Now, if you eliminate this molecule with radio frequency, and if frequency of the radiation as well as the frequency of this, if they match, then resonance occurs, then one molecule may go up, right? So NMR absorption has taken place, right? Then your intensity of the illuminating radio frequency, intensity of radio frequency radiation will be reduced. So you observe the signal, okay? This is for a simple NMR signal. This is the way you get. Later I will tell what are the complications. Remember, stronger the magnetic field, more will be the energy difference, and better is for spectroscopy, right? So that I need not explain, it is obvious, but we will move further. So we have to understand the nuclear spin, how it is there. It is like a magnet. If you apply external magnet, there can be 2 states, and energy difference corresponds to radio frequency region, and eliminate this radio frequency, then you get the NMR absorption. Okay. Now, I have given energy associated with absorption and emission. In an applied magnetic field, proton precesses with a frequency nu, which is directly related to the magnetic field. This is a precision constant. Don't worry about it now. This is the magnetic field. Okay. I have given four isotopes. I have given, there are 4 nucleates I have given: proton, deuterium, and 13 carbon. This is even, but 1 neutron, 1 proton system. 13 carbon, 31 phosphorus. This is the net angular momentum, that is I value. So these are the values. This is the magnetic field. These are the values what you get. Okay. This is the field in Tesla. 1.4 Tesla, 7.1, 11.7, 14.1. Higher the field, you get the higher is the energy gap or frequency, whatever it is. For a field of 14.1 Tesla, it is only 600 megahertz here. It's very, very low, right? And if proton is involved, if heavier atoms are involved, then it comes down. And we can calculate its wavelength, corresponding wavelength, 50 centimeters, a long wavelength. I have given here E is equal to h nu, that corresponds, this is a very low energy, and lambda corresponds to 50 centimeters. So it's a long wave, radio frequency wave number, frequency is very, very long. Okay. So what we have to remember is, stronger is the magnetic field, is better for you, or higher is the frequency if you reach, that is the best. But then cost of the NMR spectrometer will go to the sky. That is the problem. Okay. Now, even small changes, though the changes associated with are very small, they give unequivocal information. Any doubt, please? If there is a doubt, you are welcome to ask me. No doubt? Okay. For this, since changes are very small, sensitive instrumentation is required. If population in both the states, they become equal, saturation occurs, it is useless. So you should not speed up the for population. So for example, if we have a frequency of 20, excess population, that is between the ground and the magnetized state, is only 3. If it is 60, it is 9. If it is 600, it is 96. So it is better to increase the radio frequency rather than the field. Right? That is an important thing. Otherwise, your NMR signal will be lost. So higher radio frequency instruments are sensitive, but prohibitively costly. Institute like IASC, ICT have NMR spectrometers of RF 600 megahertz and above. And I tell you, an institute, research institute strength is known by total frequency. Suppose you have 10 NMR. They always tell, I have 4,500 megahertz. That means I have so many instruments with the total frequency of this one. Okay. So FT-based NMRs are capable of measuring low signals, but we will confine ourselves to 600. Okay. Now, once you excite it, you have to see what will be the relaxation process. In the relaxation, there are 2 processes. Lattice means the entire body. You don't go beyond that. Spin and lattice, they interact, they relax. That is useful for our studies. And spin will give you the structure and mechanistic aspects, but we will not go. We are using in this path. But sample preparation is an important thing here. What the sample requirement for NMR is sub-nanograms. Since you cannot make nanograms, you stop at somewhere about a fraction of milligram. Very small sample. So you dilute it with you deuterate it, right? Instead of CH4, you use the CD4, right? And it's with hydrogen you should avoid because you are using the proton NMR. Then you use trimethyl salicylate TMS as a reference material. TMS, I show structure somewhere. It is having lots of protons, but all are in symmetric position. They do not split against each other. When you go to the split point, I will show that example. So they will give an NMR signal, take that as reference. Instead of knowing the exact value, take that as reference, and that is the reference value, keep it as 0 conventionally, and rest of the changes will be measured with respect to that. So your sample should be deuterated, and then a small amount of TMS is added. Most of the cases it's TMS because it is having a quick, it evaporates very fast, so your sample retrieval will be very easy. Now, what is chemical shift? This is a concept. It's better to have once more revisit and have a clarity. Chemical shift is not chemistry. It is actually variation in the observed magnetic field. You are applying a magnetic field to create the magnetic energy states. Now, when it is coming towards the molecule, we are talking about proton, which is in the nucleus, right? And it is surrounded by electrons. Molecule is surrounded, outer place, you have the electrons. Now you are getting a magnetic field. So you have three entities which can create magnetic fields. One is proton itself, then all the molecular electrons, and then the external field. Now, these molecular electrons and proton themselves will repel and they will be in an equilibrium position. But when an enemy is coming, it will stop first. These electrons will stop this enemy first. So, in the process, this magnetic field strength will be reduced. You have to overcome. I don't know, in Hindu temple when you enter, Bhagavan may give darshan to you, but not the Panditji will not allow. A molecular electrons are Panditjis, right? So first you have to satisfy Panditjis. So the magnetic field which is approaching proton, which is going to interact, it has to overcome the in-between molecular electrons, what we call they are shielding the proton. So in the process, the field what we want to give 14.1 Tesla will not be 14.1 Tesla by the time it is coming to the proton. Therefore, there is a reduction in the applied field, or the protons do not feel the same magnetic field as applied because of chemical environment. So there is a shift in the applied magnetic field due to chemical environment. Therefore, it is called chemical shift. This, you please remember, this concept, once it is clear, then life is very easy. So, depending on the chemical environment, the extent of shift will vary. So, the extent of shift will become characteristic of the molecule. This is an important concept. Once it is clear, then life is very easy in NMR. So, applied field is not felt to the same extent by protons. That shift is due to the chemical environment surrounding the nuclei, and that is characteristic of each molecule. And that shift, because of chemical environment, it is called chemical shift. Okay. Rest of the things you can read yourselves. Okay. Now, how are chemical shifts measured? So essentially, we have to measure the chemical shift because our interest is structure. Once you want to know the structure, we have concluded already. Structure depends on the electronic configuration. Electronic configuration reflects in chemical shift. Therefore, we have to measure the chemical shift. How do we measure? Already I told you, sample has to be taken in, it has to be deuterated. Then it has to be taken in a reference material, tetramethylsilane. So all these hydrogens are in symmetric position. Therefore, they will give one single huge peak, which you call it as a reference peak. With respect to that, you measure. These calculations you can do yourself. So here, whatever shift in terms of the magnetic field is there, this can also be converted into frequency. They are related. Because we have taken in the very beginning, frequency and these are related. So you, in the measurement, you vary the frequency and measure, or you can change the field. Field changing is cumbersome. So most of the times people go for the frequency change. I will show you that picture. Now you find out the frequency change, and instead of getting the absolute value, take a ratio with respect to TMS. Then that is chemical shift. So obviously the unit will be a ratio. Since TMS is a huge one, this is small one, it is a millionth of that one. So it is called parts per million. Very small one. So parts per million with respect to TMS. Okay. Now, or with respect to applied field. I mean, it's one and the same. With respect to applied one, applied field is reflecting in the TMS. Therefore, it is a direct relation. Or if you want a formula, delta nu by applied frequency. That's all the thing. Either way, it's okay. So since we are using the megahertz, what you are measuring in terms of the hertz, so 10 power 6 will remain there. So it is parts per 1 million. Okay. Yeah, this I explained. Okay. Of course, measurements have to be careful, but wonderful. It is, I mean, it's an experience. If you students get a chance, pester the teacher and go to Indian Institute of Science or Indian Chemical Institute, IICT, Indian Institute of Chemical Technology. If you want to go, I'll tell the concerned person, they will arrange for you. Okay. One day you can have, and you can see there, if you go to IICT, there is another advantage. You have IR, UV, etc. access. Indian Institute of Science also they give, but it's a bit
complicated.
And you have one person here, one Subbareddy from Anantapur, right? I think Rayalaseema Chemistry Board is a member, right? So he's a nice person. He can arrange. I will tell him. Okay, if you want. Okay. Now, what are the chemical shifts? Like fingerprints we told there. Even the chemical shifts, there are no fixed values. There are small ranges. That range depends on the chemical environment again, right? Further, because structure, complexity of the molecule. So these are all the things what you see in organic chemistry. You don't miss anything here. Compared to, you make TMS forcibly 0. From there onwards, you have to the left side and all this. See, don't get confused with the de-shielding, shielding, etc. Right? Once it is shielded, you leave it there and move forward. Okay. So all these groups, you have the values. The moment you get the, and NMR spectrum is very comfortable, simple lines, more or less simple lines. So you can get those lines very easily. Position is, identifying position is very easy. I will show you a few spectra. So once you understand the chemical shift, range is only between 0 to 12, which is a small range. Your experimental details will, I mean, this information, what you get NMR spectra, is one of the easiest things to interpret of the lot compared to IR, compared to mass, compared to UV. UV, of course, is very easy, right? Okay, now we will move on. See, typical values I am not reading. You can read yourself. I want to give a picture that this is the range. And all are here. You won't miss a single thing. Okay. Now, how to take an NMR spectrum? Oh, 550. Okay, I'll try to go through quickly. And power break also helped delaying. Okay, again, I already told how to make sample. The point is, the solution you have to keep in a long tube, thin tube, right? Glass tube, because here you are using the wavelength, fortunately. If you talk about energy, energy will not enter the glass tube straight. Then you have to use the bare sample. So you keep that between two magnets and wind it with an RF coil. That's all the three things are there. Sample is there, tiny magnets are there, big magnet is here, RF frequency is here. Then you get the signal, which should be perpendicular to the field, and then you will get the, this you take here, and then you get the spectrum. That's all the thing. So you can use by field sweep continuous wave NMR or RF sweep continuous wave NMR. So normally frequency variation is used. Now this is a picture of the same one. Okay, there is nothing to explain, right? Now this is from here onwards, even if it takes time, bear with me, right? This is a typical spectrum of an ethanol. Here I want to tell you the meaning of non-equivalent protons. Ethanol is having CH3, CH2, OH, 6 protons are there. So we expect like TMS, there may be one peak. No, you observe 3 peaks. And the 3 peaks, and if you measure the intensity, they are in 1:2:3. That means 3 protons are coming bunching at one place, 2 protons are bunching at one place, and 1 proton is bunching at this place. That means these 6 protons are not equivalent. But 3 protons in CH3 are equivalent. That's why they are coming together. So equivalent protons and non-equivalent protons you should understand. So accordingly, you get the 3 peaks. Their area ratio tells the number of protons. And yeah. Now, this is a low resolution spectrometer. If we have high resolution NMR, then it will appear like this. The methyl one will become 3 sub-peaks. The methylene, the CH2 will become 4, and hydroxyl will remain as 1. And this is called splitting of the protons in the equivalent group. How it happens, I will explain you probably after a few minutes, because this is called spin-spin coupling, which I will explain. But remember that if you have high resolution spectrometer, you can tell how many equivalent protons are there, why it has become. The moment you see 3 peaks means you can interpret this as one equivalent group is having 2 neighbors which are influencing it. And here 2 equivalent protons has 3 neighbors. 2 equivalent protons you will have as one group, and those 3 externals will influence it n plus 1. Remember, neighbors is n, equivalent protons you consider as 1. For poor OH, there are no neighbors. H is immediately with O, therefore there is no hydrogen, no influence. So OH remains as 1, methylene remains as 4, it becomes 4, and CH3 will become 3, and the area still remains same. Okay. Now, the number of signals show how many different kinds of protons are present. In a group, equivalent protons. In different groups, if it appears, they are non-equivalent. The location of the signals show how shielded or de-shielded a proton is. That reflects in the chemical shift. The intensity, that is the area under the signal, will tell the directly proportional to the number of protons of one type. Multiplet signal reflects splitting due to spin of the adjacent protons, neighbors. This is neighbors effect. Okay. So I am giving another spectrum. Here, benzyl acetate. You know the formula, C6H5CH2, OOCH3. And here you have 3 types of protons. This is aromatic, this is methylene, and that is methyl. So you get 3 peaks. Fortunately, they don't have immediate neighbors, so there is no splitting. But why I showed this is, area and why I said no, this CH3, when C is bonded, it is CC bond here. Here O bond, here also O bond. So there is no immediate H, therefore there is no splitting. But area under these 3 peaks are directly proportional to their number. 2.52:1:1.4, right? You have to round off the full numbers. That will become 5:2:3. Immediately you say, yes, aromatic group has 5, C6H5, and methylene is having 2, that is immediate CH2, and methyl is having 3. It's clear. Straight, this sort of thing we can straight arrive at the structure. Okay. But this needs only one clue, that total number of protons. Because ratio doesn't tell the total number of protons. Now, you take the next one, phenyl acetone. This also gives very similar. But you see that methylene group is shifted compared to earlier one. And the next slide I will compare. So here also you have a ratio of 5:2:3. Again, you can arrive at, here also you see this C is bonded with C. there is no H neighbor. This C is bonded with C, no splitting. This aryl group is bonded with C, no splitting. Therefore, you get simple peaks. So this is also a similar ratio, but only important point what you have to see is here. In both the things, area is proportional to 5:3:2. But in phenyl acetone, the methylene group is having a chemical shift of 3.6. In benzyl acetate, it is having 5.1 because of oxygen bridge. In acetone, phenyl acetone, oxygen is not directly in the picture. Whereas in benzyl acetate, this is a carboxylic acid. So COOH, because of that oxygen bridge, more electron shielding, therefore applied field is felt less, chemical sheet moves to the left. Clear? So from this, such things can be obtained very easy to understand. Okay. By comparing the values, presence of O bridge can be diagnosed. Now, electronegativity, presence of double and triple bonds, aromatic groups, acidic groups, exchangeable protons, etc. influence the chemical shift values. All these things can be in the reverse screwdriver technology, we can get back. Now, what is this splitting? I already told you, if you have n neighbors, all the neighbors will spoil your head, influence your head. So yourself is one, you and your wife, or your partner, easy language. And then there are three neighbors, they will tell three stories, spoil your head. So then there will be four different signals, right? Now you just see your own story, then three people influence. Here you see, we take an example of three. This hydrogen fellow has two hydrogen neighbors. So therefore, you get 2 plus 1. Whereas this HB and HC are equivalent hydrogens, they have only one neighbor. This coupled together will get influenced by this one, so you will get only doublet. This peak will, you will get this molecule, you will get two peaks. One and area will be 1:2 because in one you have one hydrogen, in the other one you have two. Whereas this one will be split into a triplet, this will be a doublet. That is called spin-spin coupling. What is the meaning of the physics behind it? The meaning is a proton which is having a spin, other one is also having spin, so it will come and interact. In the process, if depending on the proximity, it will provide an impetus to it. It will split original signal into two. Whereas this fellow, depending on the, again, here not only spin and the distance and orientation, depending on, you remember only the tetrahedral structure. Depending on that, it will split it another way. So, though central peak will be original, it will shift on either side. You will get. That can be understood as by a Pascal triangle if you know. Pascal triangle is very simple. Each entry in the triangle is sum of the two entries above on the left and right. For example, this will be 1 plus 1. This will be 1 plus 2. This is 3, 1 plus 2. So intensities are in the ratio which can be explained by this. Intensities in a split peak. So ethyl group already explained. It will have the split into a singlet, then a quadruplet of methylene, because that CH2, two equivalent protons have three neighbors, so it will become 4. Whereas CH3, all the three you consider as 1, two methylene hydrogen atoms are two neighbors, 1 plus 2, 3. You get for methyl 3. Okay. Now we will skip next one also. But the distance between these two peaks, always they are equidistant. And that distance is called coupling constant. And that is symbol is capital J. So coupling constant tells you the extent of interaction. That is a very, very important. It doesn't depend on the applied radio frequency field or magnetic field. It is independent of that because it is the chemistry or physics of this interaction, right? J value is very, very important. It is in terms of the hertz. I am quickly going through this. I will not explain you these things. Okay. Now, these are a 4 spectra I have given for clarity to you, right? One, I have given a bromine with ethylene group. This is propylene group, depending on the strength, how you get. And an aromatic one, an alcohol with a dye substitution. So all this you read for yourself in this background. And I want you to predict the structure of this compound. You have only 2 chemical shifts. Formula I have given C5H12O2, and areas are comparable. And one thing I did not mention specifically, you will get an integral line which tells just if you take the distance between these two, that is directly proportional to the peak area. That is integration, which I have written, but I skipped it. The time was running away. So areas are in approximately 1:1. That means the moment you have area 1:1 means, fortunately we have the formula. There are 6 hydrogen each. There are only 2 groups. Only 2 groups are there, 6 hydrogens each. Okay. And you see the peaks are not split. Peaks are not split. That means not only 2 groups, there is no influence of the neighbors. They are far away. So how is it possible? Methoxy groups. Very simple. I'll tell you this. Yeah. NMR suggests that 2 groups of non-equivalent H are present. Areas are equal. Thus, each group has 6 H. Each group has one type of environment, but delta values are different. So one is, then it should be only methyl group, 4 methyl groups. So one is 1.3, which is accepted for methyl group. 3.2 for a methyl group can be there if there is an electronegative atom. Fortunately, there is oxygen. So there should be 2 methoxy groups, 1 methyl group, 2 methoxy, 1 methyl groups. The structure will be like this. Are you seeing the structure? CH3O, C is at the center, 2 CH3s and 2 OCH3s. So OCH3, OCH3 are identical. You get at 3.2. CH3, CH3, you get at 1.3. This is a standard value also. So this is the way you have to look into the moment there is no split means there is no nearby hydrogen. Neighbors are not there. The moment that clue is there, you know that 12 hydrogens you can distribute with the C rather than O. There is no OH, straight. Now, if CH3 groups, all 4 CH3 are there, one is having standard value 1.3, other one is more. So there should be an electronegative element. They are there. Therefore, it should be methoxy. That's all the structure. This takes only half minute if you understand. And such questions come in IIT entrances. I mean, JEE entrances. They come. Okay? Okay. Now, I think with that, I close. This is the structure I have given here. Picture itself I have given. And many thanks for your patient listening. I am not sorry for exceeding the time because the topic is Santa's mistake. I told her 2 hours minimum, right? And
Yes, sir, that's true.
God's hand is there, electric power failure here. And every time I tell, please don't introduce the speaker, speaker will be known after the lecture. But definitely you have to talk about your college, I understand. I am very happy that I have come, or rather, physically I have not, earlier
Yes.
I have come. I am very happy that I could deliver this lecture. I am very happy. If you enjoyed it, it is fine. If you don't enjoy, also read once more. When you get doubts, please write to me. Thank you very much. With that, my job is over.
Thank you, sir. Thank you so much.
Any doubts are there, people are welcome to ask. You have to have patience. I have patience.
But we haven't got any queries, sir, neither in the WhatsApp group nor here in the chat box.
Okay, it's rare. This is the first webinar without queries. No problem.
Okay, Vasavi, move on to the next one.
Thank you, sir. Thank you for sharing valuable information on spectroscopy, sir. It's indeed an useful session. So now I request G. Harikrishna Garu, Head of Chemistry Department, to present the vote of thanks.
Good evening, everyone. On behalf of Department of Chemistry, it is my privilege to propose the vote of thanks. I would like to express my special gratitude to our resource person, Dr. A.V. Ramana Reddy sir, who has taken time from his busy schedule to share his valuable knowledge with us today. Thank you, sir. I would like to convey my thanks to the management of St. Joseph for giving me this opportunity to conduct this national webinar. I would like to thank Principal Madam and Vice Principal Sir for their tremendous cooperation and encouragement in organizing this webinar. I am very much thankful to express my to the office staff, technical staff and organizing committee for their continuous cooperation. I am really thankful to all the participants who are present here today and for making this webinar grand success. I request all the participants to give your valuable feedback without fail. Hope you had a great session. Thank you.
Sir, if at all I receive any queries, I would be forwarding it to you, sir.
No problem. No problem.
Sir, thank you so much, sir. Once
Fine.
again, I thank you very much for accepting the invitation. And I'm extremely sorry that I couldn't give you sufficient time for the full.
No. I just joked. Shanta, it is not possible. I just joked. Either topic could have been easier.
Yes, sir.
Particularly, NMR needs explanation. Without explanation, meaningless saying that I don't have time, I cannot. Right. I am not that. So, nothing more.
Sir.
I actually, when I went through, I felt, because I made, that I made it already 2 days back.
Yes.
When I went through, I realized it, because it's last, before year I gave, it was for over about 6 lectures or so. I covered this. And as in the class, it was 15 hours each, 30 hours, 30 hours. So on the board, of course.
Sir, even for us to cover in detail in the class, it's also very difficult, sir, because we have other physical chemistry parts to be covered in the syllabus. So it's so unfair on the part of student that we are unable to spend most of the time in giving the practical examples. So I think they might have experienced today. Most of them have joined the webinar. So I think they have got some idea about how the values are helpful in identifying the functional groups and types of hydrogens and all. Thank you so much, sir, for your patient explanation and witty sparks in between. Thank you so much, sir.
That is not a prepared one on the spot.
Yes, that's true.
Hope people will not take as offensive when I said neighbors and interaction.
No. It was apt comparison, actually. Thank you, sir. Good day.
Bye. Good night.
Good day, sir.
I'll close it.
Yes, sir.